Welcome back to my course, day 6 of 28. I am admitting everyone as they come in. Okay. All right. Good afternoon. Let's see. I expect today's lecture to go till about 4 p.m. Eastern time, so that's 2 hours from now. I haven't yet built up the stamina to teach for 3 hours. It's like early in the year for me. We will cover mesh analysis. Oh, but before that, actually, logistical items. More people to be admitted. Okay, so how hopefully you guys have all sent your info to Tariq, the TA. If you haven't, please do so. It's fine. So please do that so that we can get the kits shipped. I did post the first homework. I believe it's due next Wednesday, March 3rd. I hope it's the right amount of effort and difficulty to give you guys practice in the concepts in the first 2 lectures. I'm trying to think if there was any other admin item. 4 of you still have not given permission to post on YouTube. If you haven't answered, please do, even if the answer is no. And on that note, do we send anything other than we are? No, just if you're able to come to Steinman Hall to pick them up from the TA, let us know. And that's in that case, it's all you provide. And if you are not able to come in to Steinman, provide your shipping address, and that's it. And then you'll iterate with Tariq as to no, actually, if you're getting it shipped, you just wait for it to come in the mail. You just wait anxiously as it's being delivered. And if you're coming, I need the email again. Yeah, hold on. Let me see if I think it's on Blackboard, but could be wrong. Oh, I posted my office hours. Office hours are going to be Wednesday, 10 to 11. Now, if you guys all have class, do you guys all have, by any chance, have a class during that time? Yes, no? Okay. If many of you have conflicts, I can switch it. But otherwise, that's going to be my office hour this semester. Okay. Yes. I don't know if, yeah. So if a lot of you have a conflict for Wednesday 10 to 11, then I will change it. If it's just 1 or 2 of you, you can also schedule, and I actually prefer office hours to be scheduled by email. That tends to work better, especially over Zoom. But Wednesday 10 to 11, I provided the link to the Zoom meeting in Blackboard. Okay. We are covering mesh analysis. So it's a technique for solving circuits that have current loops. And it's particularly advantageous to use mesh analysis when you have circuits that only have batteries, right? Voltage sources. We will cover how to solve circuits with current sources using mesh analysis in just a few slides. But for now, we are going to do 2 examples of solving circuits that only have voltage sources in them. So we're going to do number 1 and number 3 in the lecture. And number 2, I'll leave for you to read on your own time. Okay. So I will transition to slideshow. Okay.
Professor, I have a quick question before you start.
Sure.
You know that question you were asking us to do for extra credit or points for last class? When is that due?
There's no due date, it's just bonus. Oh, and by the way, for those of you that have sent in your answers, um, I received it. I will grade it, and if it's correct, yeah, you'll get a bonus point that will come in towards the end of the semester. But there's no due date. If you know, you can submit it now, you can submit it at the end of the year.
Okay, thank you.
Yeah, sorry, sorry I haven't responded to those that sent them in. I way too many emails every given day. Okay. Not that I'm discouraging you guys from emailing me. The too many emails are nothing to do with students. They're mostly, you know, bureaucratic shortcomings. Okay. Mesh analysis. You should always feel free to email your instructor. So I didn't want that to come off as I'm complaining to you guys about anything related to the course. Okay, mesh analysis in this circuit. So we have 2 batteries, we have 2 meshes. So the first thing that we always have to do is we have to label our meshes and assign them a mesh current. So this loop here has been labeled with mesh current 1, and this loop here has been labeled with mesh current 2. And the procedure just requires you, the technique requires you to write a KVL equation for each of these meshes. Okay, so I'm just gonna do this. I'm gonna do mesh 1 and I'm gonna get your help for mesh 2. So we're gonna start with mesh 1. We're gonna start at the bottom left and go clockwise around the loop. So we encounter a 12-volt rise, so that's indicated with a minus 12. And then the drop from here to here is equal to 2 times I1. Remember, drops are indicated with a plus. By the way, the convention that I'm using here and the book uses to write voltage rises with a minus sign and voltage drops with a plus sign, you could reverse that and you still get the same answer. Hopefully that's clear. Like, it's just a convention, and you know, if you don't like it, you're free to use the opposite convention. The voltage drop from here to here is equal to 12 times I1 minus I2. Oh, there's an email and a typo. There's a typo in the email. Is there really? Okay, let me reach out to Tariq after the class and just verify. That is his email. But CCNY has had IT issues with emails bouncing. I've been told that emails to me are bouncing back. So I will get a valid email for you guys to send that information to. Okay, so we're going around the loops. We have minus 12 plus 2I1 plus 12 times I1 minus I2. Remember, because this mesh current is going down to 12 ohm and this mesh current is going up to 12 ohm. And then finally plus 4I1. And that reduces to 18I1 minus 12I2 is equal to 12. Oh, not going to show that. All right. Who can now help me with the KVL equation for mesh number 2? I'll check my chat. You can type it in. You can shout it out.
Um,
So what's going to be, if we're going from this point to this point, there's going to be a drop. A resistor always produces a voltage drop. So what's going to be the value of the drop from here to here? We have an answer already from Christian. Okay, let's check. 8 plus 3i2 plus, we have confirmation, nice, plus 12 times i2 minus i1 plus 9i2. That is exactly right. Yeah, so it's, so the correct answer, I'll just put it up. So the drop from here to here is 12 times i2 minus i1 plus 9i2 plus 8 plus 3i2 is equal to 0. So the question for mesh 1, why is it minus 12 and not plus 12? Because if we're going from the bottom left and going up, this is a voltage rise of 12 volts, right? So you're starting from the bottom end, the negative end of the battery, and you're going to the positive end. So voltage rises, yeah, all right. And then we can put these two equations into a linear system. No problem. And so that's easy to solve. This one I would just solve with substitution. You can also use Kramer's rule, or you can just, eyeball it, compute it, a matrix inverse in your head to get the I1 is equal to 2/3 and I2 is equal to 0. This is an interesting solution in that one of the mesh currents is equal to 0. What that effectively means is that, well, actually, let me ask you guys what this means. How can it be that mesh current 2 is equal to 0? Or what does that mean? What does that effectively do to the circuit? Does anyone know?
didn't you say that the current usually takes on the path with the least resistance?
Right.
Could mesh 1 be the one with the least resistance compared to the other loop?
Yeah, but that doesn't, so current does take the path of least resistance, but that does not explain everything. No, it doesn't explain. So notice that I2 is 0, which means that this 9 ohm resistor and this 3 ohm resistor is effectively dead, right? There's no voltage drop. Let me just draw what this, and this is kind of spontaneous, so I hope I don't screw it up. Let me see. What I think this circuit looks like in actuality. This is an interesting case, actually. This is a case where this is fun. This is, I think, what effectively the circuit behaves like. This is 2, this is 4, and this is 12. So notice that I've replaced these resistors with just a wire, because I couldn't do this just by looking at the circuit. It only is apparent after solving for the values. And so because I2 is equal to 0, there's no voltage drop from here to here. And so it's effectively just a short circuit. And there's no voltage drop from here to here. That's effectively a short circuit. And so what you have, I think this is just a case where you have two batteries. Notice the two batteries they both have they're connected across a network of resistors that somehow leads to their yeah, that's interesting. I had a student ask me about this question maybe a couple of years back, and I didn't really have a I mean, I can explain the math, of course, but I still don't have a good like physical explanation for why this happens, like in words, without resorting to the math. Um, it just so happens that, so this 12-volt battery produces a current, that goes clockwise, but this 8-volt battery, so I guess what happens is the voltage between, let's see, something about the voltage across this 12 ohm resistor has to like it has to match this resistor. Okay, let me let me
Professor,
take,
can I ask you something?
sure.
You're not saying that there's no resistance in the second loop. That's not what you're saying, right?
That's
There-
right. There is actually a resistor there. There's just no current. And so when there's no current, you can just
Okay.
you don't have to, like, the product of I times R is 0. And so even though the resistor is physically there, there's you can effectively draw the circuit as if it's not there. So yeah, there is in effect a resistor here. It's just that it's not drawing any current. So that's the really interesting part about a circuit, is that this resistor and this resistor are not drawing any current. So even though there's a battery here. So there's something about, so if you notice that the 2/3,
I'm sorry, Professor. This is just like a little bit related, but because the current comes out of the negative for the 8-volt battery, it's +8, it's +8.
yeah, the way we think of this is the current would go this way, the positive charge would flow this way, right?
Okay.
But it's not actually flowing in this. And the reason is that this voltage here is equal to, so if you just focus on the 12-volt battery, it produces a voltage drop of 8 between across a 12 ohm resistor. And then basically it's like if this point is sitting at 8 volts, this is the best I'm going to be able to do. And if this point is also sitting at 8 volts, even though you can connect them with a resistor, you're not going to get any current flowing across it, because on both sides of the resistor, you have the same voltage.
Mm. Okay. All right. Thank
So
you.
you're very welcome. I will clear this and I will move on. I'm going to skip number 2. Our mesh is just a loop rule. I don't understand the question. Yes, there needs to be a potential difference for current to flow, absolutely. Because remember, potential by itself is meaningless. Like there has to be, it's like saying, I jumped from a height of 100 feet, but if I jumped onto a height of 99 feet, I haven't gone very far. So the potential by itself, the voltage by itself requires a reference point. Our mesh is just a loop rule. I don't understand the question. Meshes are just loops that don't have any other loops within them, basically. Okay, we're gonna skip number 2. We're gonna move on to number 3.
Yeah, that's why, like, if you remember, like, some people survive the lightning strike because, like, even though the voltage is really high, there's essentially, like, the current wasn't enough to kill the people, even though the voltage can jump to, like the degree of a million or something volts.
Right,
But
exactly. Yeah, that's exactly it. You know, if you need current is what is hazardous. It's one of the things, you know, the voltage that gets applied, you know, across biological tissue by itself is not hazardous. It's actually the current, the flow movement of ions is what can shut down the heart, shut down the brain, etc. But the current is voltage divided by the resistance. So there isn't a voltage. If there isn't a big enough voltage gradient, you're not gonna do any damage. Is 1 amp enough to be fatal? 1 amp is a lot. So I think I'm trying to think of when they do electroconvulsive therapy, which used to be known as shock therapy. I believe that they give you a current in the order of an amp, and that's enough to trigger a seizure in the brain. So that's, yeah. So an amp is a lot, but the current quantities that you work with in circuits, like on electronic circuits, are very small. They're in the order of microamps or maybe milliamps. So you can feel milliamp. But like if you stimulate all three of the neural engineering faculty in our department have worked on TDCS. This is not part of the course, I'm just telling you for interest. Transcranial direct current stimulation. So that's like connecting to a battery via 2 electrodes placed on the scalp. And so the current that gets passed during that is like a milliamp or 2 milliamps. And now they're going up to 5 milliamps, but that's quite uncomfortable. And you feel that like it's tingling at the very least, and sometimes like almost burning. Yeah, I think Gavin is involved. Yeah, that's Gavin's experiment. So so a milliamp is significant. So an amp is is 3 orders of magnitude times that. An amp is very significant. It's just, you know, amps are like, we're talking about like transmission lines in the order of amps or tens of amps, but you know, electronic circuits, like the subject of this course, we're talking about very small quantities relatively. Okay, here we have a circuit. We have a question or no?
Yeah, so in the last one, I didn't quite understand why was I 0. Is it because there's no voltage difference between the 8 8-volt battery and the middle? Like,
Yeah, so I mean, the real answer is I don't think you'd be able to tell that by looking at the circuit initially. You have to solve for the values of mesh currents. And only when you solve for I2 and realize that it's equal to 0, can you conclude that there's no voltage drop across the 9 ohm and the 3 ohm. And so, and when you do the KVL and see that there I2 is equal to 0, what you realize is that basically there's the voltage rise from here to here is 8 volts, which means that there's no voltage difference between here and here and between here and here, and therefore they draw no current. But this problem is actually, again, it's a little bit deceiving. You wouldn't see it right away. You really have to work out the math for the, like, if we change the values of these resistors, this would not be the case, right? So you really have to go through the KVLs to get to that conclusion. Okay, we're gonna move on to number 3. Okay, so here we have 3 meshes and 2 voltage sources, and one of the voltage sources is a dependent source. So the value of this battery here is 10 times I naught, where I naught is indicated as the current along this branch. Okay, so can anyone tell me what first of all, what is the relationship between I naught and I3? How are they related?
Equal to each other.
Very good. They are equal to each other. Remember, the mesh current is equal to the branch current, except for when the branch is common to two meshes. But the branch at which I naught is defined is only present in mesh 3, right? This is mesh 1, 2, and 3. Okay, so now let's write the KVL equation for mesh 1. So who can help me with the KVL equation for mesh 1, either on the chat or by shouting out the answer?
I have a -20
Yeah,
plus 4 parentheses current 1 minus current 3 plus
Yeah.
12 parentheses current 1 minus current 2 equals 0.
excellent. And so we had both your answer and the chat answer that just popped up are both correct.
Last one.
Yeah, I1 minus I2 for the third term here. Right, so that's excellent. All right, so we have a voltage rise of 20, a voltage drop of 4 times I1 minus I3, and then a voltage drop of 2 times I1 minus I2. Okay, what about now the KVL equation at mesh number 2?
Just gonna take a shot here. Is
Sure.
it
Negative.
It's okay, man. I get it right the first time. This is not the
Correct. I want to say the current through I2, that through this, the 2 ohm resistor,
is what?
is it IR2?
It's I2 minus I1,
Okay.
right?
And then I2 minus I3.
Yes, multiplied by what? Multiplied by 8, right? So the voltage drop, so let's start at the bottom left. So the voltage drop from here to here is 2 times I2 minus I1.
Right.
Then the voltage drop from here to here is 8 times I2 minus I3.
Okay.
And then we have a voltage rise from here to here of 10 I naught. And remember we said that I naught is equal to I3. So we can just write that as
I3.
I3, yeah. And so I think I have it, yeah. So I naught is equal to I3. All right. And then for mesh 3,
Do you mind if I try it out?
sure.
So I think it would be 4 times I3 minus I1
Yeah.
plus 4 times I naught plus 6 times I3, I think, plus 8 times I3 minus I2.
Everything's right. You don't need, there's no 4I naught term. This is not a resistor. This is just a label, right?
Okay.
So everything you said was right, but you didn't need the 4I naught,
Okay.
right?
Got it.
So it's just the 3 terms. There's 1, 2, 3 elements here. So 6 times I3, here we're starting at the top left, 6I3 plus 8 times I3 minus I2 plus 4 times I3 minus I1 is equal to 0. So now when you simplify the coefficients, so you want to write your variables on the left side, your coefficients on the right side, then you can write your system of equations in matrix form, and then you can solve this system of equations however you want. So I'm just giving you the answer here. Then I naught is equal to I3 is equal to -5. And I didn't give you the solution for I2 and I1, but you can easily get it just by solving the system. I guess the original question only asked to solve for I naught. Okay, before I move on to the next part of the slides, is there any questions about mesh analysis so far? Okay. Moving on.
I have a question actually.
Sure.
Sorry, why didn't for the for mesh 2, I believe, why didn't you set it equal to 10 I naught?
Because you're going clockwise, and this is a voltage rise from this point to this point. Right, you're going up by 10 I naught, and voltage rises get indicated with a minus sign.
Okay. Okay.
Yeah.
All right, that makes sense.
Okay, cool. So now we're gonna move on
Professor, I
to,
have a question.
go ahead.
It's always clockwise, right?
So you could do it counterclockwise. So it's like a loop. So you could go either direction, but I mean in most case I think there's a few exceptions in the course where we go counterclockwise, but again, you could apply KVL going the other way, but just as a general rule, we traverse loops clockwise most of the time.
Okay, thank you.
You're welcome. All right, so now notice that every one of these problems that we've had only had batteries. We didn't have any current sources. So what do we do with current? The problem with current sources is that we don't have any techniques for determining what the voltage drop is across a current source. And so you get into a situation like this, where how do you write the KVL equation for this mesh? Okay, so first of all, there's the case where a current source only lives in one mesh. Okay, so this 5 amp current source is only present in mesh 2. In this case, it's easy. You just say I2 is equal to -5. And then you've already solved for this mesh current. So that's actually helpful if this is the case. But in many cases, the current source will appear in between two meshes, like in a branch that's common to more than one mesh. And that's when we have to employ something called the super mesh. I didn't come up with these names, by the way, super node, super mesh. But there's nothing really super about it. In fact, in the case of a super mesh, we kind of ignore the part of the branch that has the current source in it. And so what you basically is you exclude the current source and anything that's connected in series with it. So in other words, you cut the circuit here and here. And what you're left with is just the outside. And then you still do your mesh analysis, but now you go just along the outside with mesh current 1 on the left and mesh current 2 on the right. So probably some of you are asking, well, why, first of all, why am I doing this and why is it okay to do? I mean, why is it okay to neglect the branch? Well, the reason that it's okay to do so is because KVL holds for all loops. So as long as you start and end at the same point, the sum of voltage drops and rises, excuse me, has to equal to 0. And as a result, you know, this is a loop in the circuit. And so the sum of voltage rises and drops has to equal to 0. So from that standpoint, it's valid to ignore the inner part of the circuit. However, when you do this, you're effectively losing, you're throwing away some information. And so now you're still going to have you're going to still have two mesh currents. You're going to have mesh current I1 that flows through the 20-volt battery and the 6 ohm resistor. And you're going to have mesh current I2 that flows through the 10 ohm and the 4 ohm resistor. So now you have one KVL equation, but two unknowns rather. Okay, so first of all, the definition of a super mesh, it results when two meshes have a current source in common. Right? So again, these two meshes, I1 and I2, have the 6 amp source in common. So you have to create what's called a super mesh, which is really the joining of meshes 1 and 2. Okay. So we create a super mesh as the periphery of two meshes. And the reason we have to do this is because mesh analysis applies KVL, but we do not know how to solve for the voltage across the current source.
Professor,
Yes.
can if you go back to the other slide, can a super mesh I guess be if you have like if there was another section of the circuit, could you do a super mesh for only two and then like and a different KVL equation for another part?
Yeah, that happens a lot actually. Yeah, it's a good question. So yes, that happens quite a bit where you have three meshes and only two of them have a current source in common. And then what you do is you create a super mesh between those, but then you leave the other one intact. And you'll see examples of that, I think, in this lecture. Okay. Okay. So now we are, okay. So we know that the outside of the circuit, which we can call a super mesh, has to obey KVL. So we're going to start off the bottom left and a voltage rise of 20. So that's minus 20 plus 6 times I1 plus 10 times I2 plus 4 times I2 is equal to 0. There you go. That's easy. That's easy enough. Now the question is, how do we get another equation, another source of information for I1 and I2? And the way we do it is we apply KCL at the super mesh. So look at this picture. Look at this T juncture, this inverted T juncture over here. We have I2 flowing in, 6 amps flowing out, and I1 flowing out. So in other words, at this point here where my cursor is, we can say that I2 is equal to 6 plus I1, right? So just to make this clear, right, we have this current flowing in, and then we have these two currents flowing out, right? And this is equal to 6. Sorry, not 6. This is equal to I2. All right. There we go. There's an eraser. Very nice. Right, so the black has to equal the sum of the two reds. That gives you KCL. So now we have two equations and two unknowns, which we can solve for I1 and I2. So in my opinion, super meshes are easier to kind of visualize and understand in supernodes. Basically, all you're doing with a super mesh is you're ignoring one of the branches, and you're just applying the laws of conservation of energy and conservation of charge to the remainder. Okay, so the two properties of a super mesh. So the current source in the super mesh is not ignored because it gives us the necessary information to write the KCL equation. Right? So this KCL equation requires the shared current source. And a super mesh has no current of its own. In other words, I don't like that statement. I don't like these properties of super nodes, super meshes, but basically, if I had to rewrite this, I would say that what a super mesh is, it's a statement that KVL holds for all loops in the circuit. The 2 ohm resistor, remember, so right. So if I have let's see, I'm enjoying the drawing, so I'm just going to keep drawing. So if I have a circuit, this is right. And now I'm going to cut the circuit here and here, right? Even if I wanted to say here and here. Let me see if I can undo. No, but I can erase. Right. Let's say I cut the circuit here and sorry. Okay, let me see. Draw. Color. Okay. Now, oh no, my eraser. If I cut the circuit at this point and this point, so you can argue that, well, I still have that resistor. Then my circuit looks like this. Right? Looks like this. I've taken out the current source. Well, this resistor is here, right? But there's no more current across it. So the voltage drop across this resistor is just equal to 0, right? And so the voltage drop is equal to 0. You can just replace it with a wire, right? So it's not like we haven't really ignored it. It's just that if there's a resistor with no current, there has no voltage. Okay, good. Okay. So the super meshes do require, so any circuits that have a current source that are common to more than one mesh, to solve that circuit with mesh analysis, you need to apply both KVL and KCL.
Wait, Professor, can you go back a slide?
Yeah.
For I2, why is it I1 plus I6 if I2 is going the same direction as 6 amps?
So you're looking at, oh, I lost my cursor. Hold on. Oh, seriously? Let's see if I can figure this out. Oh, I got it back. I think, what's the solution to this? Give me just 1 second. Give me a second. It's there again. There's some kind of a, I don't know if I should. No, I blame Microsoft. I was gonna say I don't know whether I should blame Zoom or Microsoft. I'm just gonna go out on a limb and blame Microsoft for this bug that happens when you do full screen slideshow on the PowerPoint and annotation on Zoom. There's some kind of a weird bug that happens and you lose your cursor. So I blame Bill Gates personally for that bug. Okay. I'm sorry, I got a little bit sidetracked from your question, which was what happened. So you're applying KCL at this node, right? So you have I2 going this way. And that's so into this node, you have I2 is flowing in, I1 is flowing out, and 6 is flowing out. Right? So I2 and 6 are not, I2 is going into the node, but 6 is leaving the node.
Got it. Thank you.
You're welcome. Clear. All right. Let's do, I think we're going to do an example. Right. So let's do an example with a super mesh. So the question is to find I1 to I4. So find I1, I2, I3, and I4 using mesh analysis. Okay. And so here you see an example where we have a super mesh. Right? We have two super meshes and we can combine. So we have a super mesh between meshes 1 and 2 because of this 5 amp current source. And we have another super mesh between I2 and I3 because of this 3I0 current source. And so we can just create one large super mesh, this L-shaped mesh here. Right? And we still leave I4 intact. We still leave that mesh alone. And we're still going to use the information from that. But so now the question is, how do I write my KVL equation for this L-shaped mesh? Right, so I'm going to need 4 equations to solve this problem. So who wants to take a stab at coming up with the KCL equation for this L-shaped mesh here? Excuse me.
Can I try, Professor?
Sure.
We would place the node at the intersection for all three currents, which is after 5 amp. There's a point. Wait, can I draw on it?
Oh, can I? Is that something that I can allow?
I think so.
Okay. Give mouse keyboard. Yeah, that would be awesome. Can you say something so I can see your name? Sorry. Oh, nice.
Did it
This
go?
is my first time.
Oh, I don't know. This is my first time doing it too.
Yeah.
Exit full screen. Oh, I have control over it. I don't know how to draw it with it because there's supposed to be an annotation on the
Okay.
side.
See it now?
I can control your keyboard layout.
All right. Let's.
Okay, I'm on
why,
good.
why don't we just so remember I'm asking for the KVL, right? The
Mhm.
KVL equation is going to ignore the 5 amps and the 3I0,
Mhm.
right? So why don't we write all the voltage drops that are going to happen along this path? Right, so what's going to be the value of the voltage drop across the 2 ohm resistor? Let's start there.
2I1.
Right? And then where's the next voltage drop?
A 4 would be, oh my god, I didn't realize. 4I3
Right? And then what's the voltage
minus,
drop across
oh
the
wait,
8
no,
ohm?
plus 8I4. Wait, would we combine all the currents?
So remember the current, here you have a situation where the 8 ohm resistor
Mhm.
is common to mesh 3 and mesh 4,
Mhm.
right? So what's the current flowing from here to here?
Oh, I3 minus I4.
Exactly.
But aren't we like combining all the currents in a
No,
way?
no,
we're
we're
just ignoring the
cutting-
line.
Yeah, you're just like, you're pretending as if this current source doesn't exist and
Uh-huh.
this current source doesn't exist. And you're
Okay.
going around the L.
Okay. Okay, so 8
They're almost
I3
there.
minus I4 and plus 6 I2, and that's it,
That's
right?
it. That's it. That's excellent. Yeah, so 2I1 plus 4I3 plus 8 times I3 minus I4 plus 6I2 is equal to 0. That's great. Okay, so now we have to do KCL at points P and points Q. So let's start with point P. What's going to be the KCL equation over here?
Would it be I2 equals I1 plus 5M?
Excellent. I2 is flowing in. And then what's flowing out is I1 plus 5. That's great. So now let's do KCL at point Q. Yeah, so
I2 equals to I3 plus 3I naught.
yes, excellent. I2 is equal to, so I2 is flowing out and 3I naught plus I3 are flowing in. Right, and so we also know that I naught is defined over here. Right, so remember, this is a dependent current source. And so its value is dependent on this current, where the current here has been defined by I naught. Notice that I naught is just opposite of I4, right? It's in the same mesh, but has the opposite direction. And so we negate it. So in other words, we can substitute negative I4 for I naught in this equation. So now we have 4 unknowns and 3 equations. And so we need to come up with one more equation. And the way to get that is to apply KVL to mesh number 4. So who can tell me the KVL equation for mesh 4 here? Starting at the bottom left.
For mesh 4, would it be 8 times I4 minus I3?
Yeah.
Plus 2I4?
Yeah.
Plus 10?
Yep. Excellent. Right, so now we have our fourth equation, and again, with a 4-dimensional system of equations, you would almost surely want to use some kind of a numerical technique. You wouldn't want to solve it by hand, although you could solve it by hand, but it's more painful. And so, here's where you would use a programmable calculator or MATLAB or something like that. We are going to do this practice problem. This is a good one. And we are being asked to solve for I1, I2, and I3 using mesh analysis. Okay, so I'm going to redraw the circuit here. So the first thing that I want someone to tell me is, where is the super mesh gonna, what is the super mesh gonna look like for this problem?
Is it between I1 and I2?
It is, right? It is between I1 and I2. Right, so you can draw this L-shaped, again, this L-shaped super mesh. And which brings us to the KVL equation around this L-shaped mesh. So who can take a stab at writing or saying the KVL equation for the super mesh? So we have -6, right? To go from here to here, or -6. No, nothing up here, so we get to this point. And now what? What's the voltage drop across the 2 ohm resistor equal to?
2 times I1 minus I2.
Try again. Almost.
So it would be I2 minus I1.
No, it's this resistor, right? The one that I'm pointing to.
Yeah.
So it'd be 2 times I1 minus I3.
I3.
Yeah, because
Oh, because okay.
right? Because this resistor is common to mesh 1 and mesh 3.
Okay. I didn't even catch that. So then it would be, let me see, it would be plus 4 times I2 minus I3.
That's right.
Okay. Plus 8 times I2 plus 1 plus I2 minus I1.
No, because this is being cut. You're actually done after you got past the 8 ohm resistor.
Why is that?
Because you're going around. So if you Bill, you're gonna get me again here. I'm about to reproduce your bug. So you're going, this is a tricky one. This one causes a lot of confusion. This problem, I remember this historically. So this is the mesh that we're talking about here. And notice, so once you get past the 8 ohm resistor, you're in the clear. You're back to the beginning, right? There's no resistor anymore. You're not going up here, right? Because you've made a cut here and here.
Okay, so basically like that resistor really isn't in use anymore.
That's right. It's not in the super mesh.
Okay.
All right. So now we have, so yeah, again, -6 plus 2 times I1 minus I3 plus 4 times I2 minus I3 plus 8I2 is equal to 0. Right? So that gives us one of our equations. We need 2 more equations. So who can tell me the, let's see, let's do the KCL equation over here. It's probably the easiest point to do the KCL. Someone's had enough. 3 plus I2 is equal to I1. That is correct, Christian. Yes. Excellent. That is our oh, I went out of order, but it's okay. So at the super node is what I was asking for. 3 plus I2 is equal to I1, right? So there's 3 flowing in, I2 flowing in, and I1 flowing out. So that's this here. And then the corner loop, what I referred to as the corner loop, is this mesh here, right? So just because I really am enjoying this drawing feature provided to us all by Zoom. No thanks to Microsoft. Ah, why is it not letting me? Let's see. I barely see the difference between those two colors. Right, so this is the corner loop here that I've drawn in green. Right, and so let me get rid of the toolbar. So across the 2 ohm resistor here, we have a drop of 2 times I3 minus I1. So going from here to here, we have a voltage drop of 2 times I3 minus I1. Then a voltage drop of 2 times I3. And then finally, a voltage drop of 4 times I3 minus I2. All right. Okay. So now we have our three equations, which we can put into a matrix form. And we can solve them for I1, I2, and I3. Okay, so is there any questions about this problem? All righty. Let's move on. It's eerily quiet. Go ahead.
Could you go back one slide first? Because it's
Sure.
yeah.
Back one more or this one?
This one. So when you made the super node, I was just wondering, is that with the super mesh or is that without the super mesh? Because
Oh, I'm so sorry. This is a typo. It's funny, like how many, let me just fix that. Yeah, thank you for catching that. That's just a typo. Yeah, it's funny. This is year 6 and you're the first person who caught it. Yeah, it's super mesh. So, but it's you know, more descriptive at bottom of super mesh, right? So what we're trying to say here, I was trying to say at this node of the the bottom node of super mesh.
okay. I was wondering, like, could you like mix them?
No. You
Like,
don't.
how do you have a super node and a super mesh?
You're either doing, if you're doing nodal analysis, you can have super nodes. I'm sorry, I forgot to share a screen. If you're doing nodal analysis, you can have a super node. If you're doing mesh analysis, you can have a super mesh. You'll never have both of them together because you're not going to do both nodal analysis and mesh analysis at the same time.
Okay. Is it just we're not doing it in this class, or you just can't do it at all?
I don't think you could ever have. I mean, could you? I mean, you're either solving for voltages or for currents. So I mean,
Okay.
I don't think. Although who knows? Maybe there's some case for you, but definitely not in this course.
Okay.
All right. You're welcome. Is there any other any questions? Let's see. So weird. Is it possible to do KCL at node connecting the 2 ohm, 4 ohm, and 3 amp 2 ohm? Yeah, that's a good question. Yes, it so I'm gonna write it down just on my pad here. Yeah, it will be harder. It will definitely be harder. And the reason is that this branch here is a mixture of I1 and I3. But I still think you will get the right. I still think it will be correct. Let me just write this down. It will be no, actually, you know what? I don't think it is. I just tried to do it and it wouldn't work. I don't think it's possible actually. The reason is, so I'll show you. If you want to do it at this node, the current going from here to here is equal to I1 minus I3. Or actually, wait a second. I didn't do it right. Let me do it again. I1 minus I3. And then if it works, I'll show it. I'll annotate it. Is equal to 3 plus I3 minus I2. Yeah, it would work. So it will be so it'll be I1 3 plus I3 minus I2 is equal to 3, which is equivalent to I1. Oh, no, why would it give us the opposite answer? Let's see, I1 minus I3 plus I2 minus I2. Yeah, I mean, I don't know. It's a very good question, and I'm sorry that the answer that you get here seems to be the opposite of this. So I must have done it wrong, but you should be able to do it. It's just the problem with doing is the reason that you want to do it at the bottom is because all three of these branches have, this branch here has multiple mesh currents still active, and same with this branch. And so that's the problematic thing. And so I just tried to do it here, but it gives us the wrong answer. So actually now I don't know for sure if it will be correct. In principle, you should be able to write KCL at this node here and still get the correct answer. But I haven't demonstrated that here. So that is kind of an open question. But I guess for the sake of, all the questions that you will encounter in this course, you just want to apply KCL at the point in the super mesh where there is no shared branches. I think that's really important. All right. Let me get rid of the annotation and let me move on to. So there are cases where you can write the equations for nodal mesh analysis just by looking at the circuit. So the rest of this lecture is just about how to solve by inspection. What we mean by inspection is visual inspection. Just look at a circuit and write down the equations immediately. So to demonstrate, we're going to go through a couple of examples. And so remember, this was a circuit that we started with for nodal analysis. And if you remember, the system of equations that we derived by applying nodal analysis here and here is what's written. So if you don't remember, you just go back to the lecture would have been day number 4 of the course. And so notice one thing, look at node 1. Look at that G1 and G2 corresponds to this conductance plus this conductance. So those are all the conductances that are flowing into node 1. And G2 and G3 are all the conductances that are flowing into node 2. And notice that the negative G2 corresponds to the conductance that is in between nodes 1 and 2. So you could just look at the circuit and for every node, sum up all the conductances that are connecting to it. And those are the diagonal elements. And for all the off-diagonal elements, you would just write negative the conductance that's connecting those two nodes. So one thing, trying to get to my toolbar here. So this is row 1, row 2, column 1, column 2. So this element of the matrix here is equal to minus the total conductance between nodes 1 and 2. And this value is the sum of conductances between nodes 2 and nodes 1. So this matrix is always going to be symmetric because the conductance between nodes 2 and 1 is obviously the same as the conductance between nodes 1 and 2. And this value here is the sum of all the conductances that are flowing into node 1. And then similarly, the on diagonal terms of the matrix are all the conductances that are flowing into node 2. Yeah, it's really a shame that linear algebra is not taught. I think linear algebra should be like pretty much the first course that every engineering student takes. I've lost my cursor again. Yeah, so it's G2 is negative because it's whenever it's in between two nodes, it becomes negative. All right, let me see what the solution is. If I can remember. PowerPoint. Nope. Zoom. Okay, clear all drawings, get rid of it. All right. So that's nodal analysis with current sources. Yeah, that's right. You can't do this with super nodes or super meshes. All right. So each term on the right-hand side is the algebraic sum of the current sources entering the node. So notice that this term here, the I1 minus I2, right? So entering node 1 is I1, and exiting node 1 is I2. So that's why it's I1 minus I2. And then entering node 2 is I2, right? So this I2 corresponds to this current flowing into the node. Oops. And the I1 is flowing in, and the I2 is flowing out of node number 1. So I don't want to spend too much time on this because I don't like techniques like this that like they're essentially, this is like a recipe that is valid. It will get you to the solution, but it doesn't really teach you. I like working from first principles, and I would prefer for you guys to work from first principles. Okay, so having said that, the recipe is to write a matrix of conductances and a matrix of current on the right-hand side, and you're solving for the node voltages. And so the diagonal elements of this matrix is equal to the sum of the conductances connected to that node. Someone's had enough. And the off diagonal elements is negative of the sum of conductances between nodes K and J. So for example, this element here, G1N, will be minus the sum of conductances between node 1 and node N. Oh, you want back. I'll let you in. And then G21
fundamentally is, let's say you have
G21 is equal to minus the sum of conductances between node 2 and node 1. And so really the best way to understand this, and so finally the IKs on the right side is just equal to the independent current sources directly connected to node K. So let's just work through an example, and then I think you guys will understand exactly how this works. So the idea is this is all by inspection. You don't have to work from KVL and KCL. You don't have to work from first principles. You can just look at the circuit and write down the equations. Okay. So, and now we're going to do the same thing we're going to have like a recipe for mesh analysis as well. And so this was our first mesh analysis circuit. So this is a typo, by the way. This should say I2. I don't know. I blame it on the book. And so remember that this was the system of equations that we got for this circuit. Notice that R1 plus R3 is the sum of the resistances along mesh 1. And R2 plus R3 is the sum of resistances along mesh 2. Notice that R3 is the common resistance between meshes 1 and 2. Right? So the on-diagonal elements are the sum of resistances along the loop, and the off-diagonal elements are the negative of the common resistance between the two loops. And finally, the voltage, notice that V1 is in mesh 1 and V2 is in mesh 2. So why is this indicated with a positive sign and this with a negative sign? Well, the reason is this is a voltage rise going in the direction of the clockwise current arrow, and this is a voltage drop going in the direction of the clockwise current arrow. And just in case this is unclear, you can always arrive at these equations by applying KVL. In fact, I will prefer for you guys to use KVL. You're going to learn more. And it's just, you know, these mnemonics, we teach them to you, but it's for me, it's a less, it's a less illuminating way of solving circuits. All right. So let's, so again, when you're doing mesh analysis, you can write down a matrix of resistances and a column vector of voltages. Yes, and this is a question I get every year. Sergio, the reason is, remember, those are the rules that apply when you're writing the KVL equation, when everything is on the left side of the equation. But now we're moving the voltages to the right-hand side. And so when you move it to the right-hand side of the equation, you switch the sign, right? So the negative voltage rise and positive voltage drop is when everything was on the same side of the equation and the right-hand side was equal to 0. But now we've moved the voltages over to the right-hand side. And yeah, good. All right. So this is just a big matrix vector equation. Ri is equal to V. And again, the on-diagonal elements are equal to RKK, and it's the sum of the resistances in mesh K. And the element at row K, column J, is negative the sum of the resistances that are in common between meshes K and J. Okay. The I's are what you're solving for, they're the mesh currents. And each element of vector V is the sum of the independent voltage sources in mesh K, with the voltage rise now treated as positive. All right. We're going to do a couple of these. They're not difficult to do. So we're going to start off with this one. So this is good. First of all, how many, what's going to be the size of my G matrix here? How many rows and columns will my big matrix have? 4 by 4, excellent. And so let's start getting the diagonal elements, all right? The diagonal elements are equal to the sum of the conductances flowing into each node. So flowing into node 1 is 10 ohms and 5 ohms. And remember, conductance is the reciprocal of the resistance. So it's 1 over 10 plus 1 over 5, which is equal to 3/10. G2, it's 1 over 5 plus 1 over 8 plus 1, right? Don't forget about this 1 ohm resistor that is also connected to node 2. So that's equal to 1 3/8. The third node here has a 4 ohm, an 8 ohm, and another 8 ohm. So the reciprocals of 8, 8, and 4 give you a sum of a half. And finally, the fourth node has a 1 ohm, an 8 ohm, and a 2 ohm connected to it, which when you sum up the reciprocals gives you 1 5/8. And so those are the diagonal elements. And now the off diagonal terms, you just have to look at between every pair. So when you have 4 nodes, you have how many handshakes do you have between 4 people, right? It's 4 times 3 divided by 2. So you have 6 handshakes, is that right? How come I see more than 6 numbers here? Right, because they've repeated G1, they've repeated G1, 2, and G2, 1. So when you have 4 unique nodes, you have 6 unique pairs, right? So G1, 2, so node 1 and between nodes 1 and 2 is a 5 ohm resistor. And so G1, 2 is equal to negative 1/5, which is equal to negative 0.2. There is no resistance between nodes 1 and 3. They are not connected directly. Also, node 1 is not directly connected to node 4, and therefore both G13 and G14 are equal to 0. What about G23? Well, between nodes 2 and 3, there's an 8 ohm resistor. So we know that G23 has to equal to negative 1/8. And nodes 2 and 4 are connected by a 1 ohm resistor, right? The conductance of which is 1, and therefore G24 is equal to negative 1. And so find the last unique pair is between nodes 3 and 4, right? So nodes 3 and 4 are connected by an 8 ohm resistor whose reciprocal is 1/8, and we stick a minus sign in front of it because this is an off diagonal term. Okay, and now finally, let's look at the currents. There is a 3 amp current flowing into node 1. Node 2 has a 1 amp current escaping and a 2 amp current escaping. So its value is going to be -3. So the sum of the currents flowing into node 2 is -3. I3 does not have any currents flowing into or out of it. And I4 has a total of 6 amps, 2 over here and 4 over here flowing into it. So now we have all the information that we need to write down the system of equations, right? So for example, the 0.3, these 4 numbers are the diagonals. And for example, G12, which we found as negative 1/5 ohms, is the element at row 1, column 2 of the matrix. So for G32, for example, is the element at row 3, column 2 of the matrix. Right? So all we're doing is figuring out the coefficients and then plugging them into the correct spot. So 3 amps, -3 amps, 0 amps, and 6 amps. So now you have 4 nodes and 4 unknown variables with 4 equations, and you can solve them. You could solve this system of equations however you like to solve for V1 through V4. All right. Does anybody have questions about how we arrived at this system of equations?
Professor, can you please re-explain the part of the diagonal terms of G?
Yeah. So for the diagonal terms, you're looking at just a single node. So node 1, it's connected to a 10 ohm resistor and a 5 ohm resistor, right? So the conductance is 1 over resistance. So it's 1/10 plus 1/5 with a positive sign. And then for node 2, it has 3 resistors that are connecting directly to it: a 5 ohm, an 8 ohm, and a 1 ohm. So it's 1/1 plus 1/8 plus 1/5. Right, so you're just summing up, you're converting every resistor to a conductance, and then you're summing up all the conductances that are directly connected to that node, right? So G22 is over here. It's row 2, column 2 of the G matrix. Okay, is there any other question? You're welcome. All right, I'm gonna get your help on this. Who can tell me the number that belongs in row 1, column 1 of this matrix? So this is node 1 over here. Which resistors are connected to node 1?
Is it gonna be 1/5 plus 1/10 plus 1/1?
Excellent. So that's 0.1 plus 0.2 plus 1, so it should be 1.3, right? And then similarly, for node 2, it will be 1/5, which is 0.2. For node 3, it will be 1/1 plus 1/4, so 1 1/4. And node 4, it will be 1/4 plus 1/2, which is 3/4. So who can tell me the value over here at row 1, column 2? How much resistance is connecting nodes 1 and nodes 2? Oh, we have a chat answer. Hold on.
1/5 a negative.
Yeah, sorry, negative, that's right. It's negative 0.2, right? And then similarly, for example, between 1 and 3, there's a 1 ohm resistor. And so it's -1. And so let's look at some of the other, and then the only other connection that has a resistance is between nodes 3 and 4. It's -1/4. Okay. And then to get the how much current is flowing into node 1? What's going to be the value over here? 0 is correct. Thank you. Right. And there's 3 amps flowing into node 2 because there's the 1 and the 2. There's 1 amp leaving node 3. And there is, let's see. Is this right? Yeah, and there's 3 amps entering node 4. Here. That the 3 here corresponds to this 3 amp source hitting node 4. All right, last 2 questions. We're gonna write the mesh current equations by inspection. It seems like a lot, but it's actually not. It's not that bad. It's just a lot. So I think what I'll do is I'll kind of walk you through this example, then I'll get your help on the second one. So let's start off with mesh number 1. Remember, for mesh current equations by inspection, we have to sum up the resistances in each loop. So how much resistance is in mesh number 1? What's the total resistance in mesh number 1?
9 ohms.
9 ohms. Yeah, right. And similarly for mesh 2, it will be 2 plus 2 plus 1 plus 1 plus 4 equals 10. Mesh 3, it will be 4 plus 2 plus 3 equals 9. For mesh 4, it will be 8. And for mesh 5, it will be 4. So the next step is super easy. It's just looking between every pair of meshes and figuring out how much resistance is common to them. So let me ask you this. In a room full of 5 people, how many handshakes are there? How many handshakes in a room full of 5 people?
10 handshakes.
10. Excellent. So how did you get that?
So 2 hands per person.
No, that's wrong. That's not the right way to get it, but you did get the right answer. But seriously, I mean, let's think of, well, I can tell you the formula actually. I'm not gonna make you guys suffer. I give you credit for getting the correct answer. It's n times n minus 1 divided by 2, right? So if you have 2 people, it's 1, 3 people, it's 2, etc., etc. So it's n times n minus 1. So there's 10 handshakes here. So you have to look at between those 10 pairs of meshes, how much current is in between each pair. So for example, between mesh 1 and 2, you have 2 ohms. So the value will be negative. So the value on row 1, column 2 of the R matrix will be -2. A lot of these will be equal to 0, right? There's going to be a lot of zeros. Anytime you have 2 meshes that are not connected, you'll have like, for example, mesh 1 and mesh 4, you'll have a 0, right? And everywhere else, you'll just sum up. Let's look at, see if there's any meshes that have 2 resistors in common. I don't think there is. Yeah, all of these just have a single resistor in common. So for example, 4 and 5 will have a 3 ohm in common. So R4 5 is equal to -3, right? And then the last thing that you do is for each mesh, you sum up voltage rises, right? So for example, for mesh 1, the sum of voltage rises is 4. For mesh 2, it's 10 minus 4. For mesh 3, it's 6 minus 12. For mesh 5 is -6. And then again, you just stick your numbers into the right slot of the matrix / vector, and then that's your system of equations. So you can apply this rule whenever you do not have A, dependent sources, and B, super meshes. So those 2 things have to be true to apply this. And if you're ever in doubt, just go back to first principles. Okay, you will never be, I don't think on an exam, you'll never be asked to solve by inspection. You'll be asked to solve. So you can always go back to first principles. All right. Last question. Who can tell me what the value is going to be at row 1, column 1? It's quieter than it. Oh, I was going to make a bad simile there. 170, excellent. Right? The sum of 50, 40, and 80. What about what's going to be the value at row 2, column 2?
80.
80 is good. What about row 3, column 3?
50.
50, and then 90 and 80, right? And then the off diagonals, what's going to be the value of row 1, column 2?
-40.
-40, right? And then the other ones, I'm sure you guys know how to do this for. So for example, mesh 1 only touches meshes 2 and 4, right? And that's why the value at row 1, column 3 and row 1, column 5 is equal to 0. Right? For example, it has the 80 ohm is common to meshes 1, meshes 4, and that's why you get the -80. And then again, let's look at the sum of voltage rises for mesh number 1 is 24. And then the other ones you just sum up. There's 0 voltage along mesh 2. There's -12. There's a 12 volt drop, which is written as a -12 on the right hand side of the equation. There's a 10 volt rise in mesh 4 and a 10-volt drop in mesh 5. All right. Is there any questions about anything that we've done in the course up until this point? All righty. I'm not going to start lecture diagonal once more. Sure. Off diagonal. Yeah. Again, I know that I think you guys would really benefit from a linear algebra course, like, I don't know, elementary school. I would start as soon as possible in honestly. They're teaching programming now in elementary school. I don't see why they can't be teaching matrices. Maybe that's a stretch, but I really feel like linear algebra and programming are like so critical nowadays. Okay. Sorry, I'll be saying that a few more times in the course. So this is row 1, 2, 3, 4, 5. This is column 1, 2, 3, 4, 5. So the rule is the diagonal terms are always going to be positive. So by the way, if you look back at every mesh question that we did, what you'll notice is that the diagonal terms are going to be positive and the off diagonal terms are going to be negative. And so the rules for the diagonals, you sum up the total resistance along mesh 1. So mesh 1 is here. All right, so the sum is 50 plus 40 plus 80 gives you 170. For mesh 2, it's 40 plus 30 plus 10, which is 80. Mesh 3 is 30 plus 20, which is 50. Mesh 4 is 80 plus 10, which is 90. And mesh 5 is 20 plus 60, which is 80. So now let's do the off diagonals, right? So let's do between meshes 1 and 2. So which resistors are common to mesh 1 and mesh 2? Well, it's just this one here, just the 40. And so you write that with a minus sign. That's the rule. Again, this is why I don't like I don't like techniques where you just do it because that's the rule. I prefer to have a physical reason for everything. Anyhow, I digress. What about between nodes between meshes 1 and 4? Well, there's this 80. So you again would write out with the minus sign. And let's look at between row 4, column 2, right? Why is this minus 10? Why? Because meshes 2 and 4 have a 10 ohm resistor in common. All right, let me see if I've answered your questions. Got it. Okay. Yes, the off diagonals are always negative. Now, again, this is no super meshes and no dependent sources. If you're ever unsure, just go back to first principles and write the KVL equations from first principles. But if you're in a situation where you only have batteries and no current sources shared between meshes, you can do this by inspection. I think what you'll see is that when you do a bunch of practice problems, you know, and you can get those from the back of the book, it will just come natural. It will just come naturally, and you'll start to be able to write the KVL and KCL equations pretty quickly. Okay, is there any other questions? So in that case, I just want to say that anything I said about the Microsoft Corporation was purely in jest. And at the same time, the views that I've expressed are not indicative of the views of City College, the City University of New York, anyone else that pays me. I will say, rest in peace, Paul Allen. Bill, I'm just joshing with you, man. I love your products. I use them all the time. Bye, guys. See you next week.